Welcome to lecture 6 of quantum physics for non-physicists. And today is the 1st of October, 2020. And today we will recap just one small thing about what we did last time. So the 1D space and properties of x and p and the wave function. And we'll expand a bit more on the last thing we did, which was the commutator of x and p, and see applications of this. And then we will jump right into dynamics in 1D space, which means we're going to take the Schrödinger equation and we're going to apply it to an actual Hamiltonian of a particle in a line. Okay, and we'll only get started with this today, and then next week we will we'll develop this a bit more. And the relevant chapters from the Schumacher and Westmoreland book is chapter 10 for what we'll do today, only a little bit, and then we start with the beginning of chapter 11. Okay. And then later on we'll come back to chapter 10 and so on. And our daily analogy is power escalation in the way we use quantum mechanics. So there's some fiction where we have a little bit of magic, and we start with like seeing how characters apply this magic in a very standard way. So for example, in the last Airbender, you have Katara who can bend water, and she applies it to the waves in the sea or ice. And then later on, you start thinking about, oh, how else can I use this power? What else can I apply this to? And she has things like, at some point, applying it to the water that lives in the grass, for example, or eventually to the water that runs in our blood. And then you see that suddenly you can do much, much more with this power than you thought originally. So the same is true for quantum mechanics. Right now, we'll see a very kind of tame version of it, but later on, and if you stick to it for the next semester, you see that you can apply it, for example, to time, because this parameter t in the Schroding equation is a classical parameter, but it's not something we can actually measure in real life. In real life, we only measure clocks, and clocks will ultimately be quantum systems. In the same way, directions, you measure directions via a compass or via gravitation, for example. But in the end, like the Earth itself is a quantum system. And what happens if directions itself are quantized? And this is a very, very active field of research. It's super cool, and this is some of the things I work on. So if you stick to quantum mechanics for long enough, you'll get to see all of this. But not today. Today we only just get started. So a little bit of housekeeping. Someone asked about the problem sheets versus the lectures, because the lectures so far have been more like the mathematical framework, where the problem sheets are more specific examples. And this is by design. And don't worry if you cannot solve right away one problem sheet, or you read the solutions and think that, oh, I could never have guessed this. As long as for now, once you see the solutions, it makes sense given what you know from the lecture, this is enough. And then later on, we will treat these physical systems also in the lecture. Okay, but for now, it's more just to give you small examples of how this could be applied. Someone asked me about the exam. So, it's going to be a written exam, and before the end of the semester, we will publish like an example exam. But for now, you can maybe know that it will have similar format to the exercises. So if you keep doing the exercises, then this will help with the exam. Of course, that if you cannot do an exercise now because you know how to start, don't worry about this. What matters is that at the end of the semester, you could solve all the exercises. Okay, but we'll talk more about this when the time comes. So don't worry too much. Okay. So let's get started. And sorry, I just forgot to put the chat up so I can see if you have questions. Very good. Okay. So why do we care about the wave function so much? So for example, last time we saw how some operators acted on the wave function instead of saying just the matrix representation of this. And the reason for this is that, well, the wave function corresponds, like we saw, to just expanding a state on a basis. Again, all the integrals are from -infinity to infinity unless said so, because again, this is the identity. And so, and the idea is that these are the coefficients of an expansion which means that if you know how the wave function transforms under some transformation or some operator, then you know how this whole basis transforms under this operation, right? Which is normally everything we need to know. Which is why sometimes we have some operator A and we say, well, it transforms the wave function like that. So for example, we saw that P takes the wave function and transforms it into something like this, right? Okay, and this will be useful later on. So sometimes, for example, in the examples we see later, the dynamic examples, instead of carrying around like the whole state, we just take the basis as implicit, and we just work directly with the wave function. Okay, but just keep in mind what it means. Okay, this was one thing. The other thing was the commutators. If you watch a lecture live, watch the last 5 minutes of the video recording of it, because I did the commutator much better there. So we saw that x and p is given by the identity times this complex constant, and I told you that this will be useful because later the Hamiltonians will depend on x and p, so we want to see how this how these things evolve, and we'll see this today already. But before, we'll need an ingredient, which is to know, well, what if we have some function of x? How does it, what's the commutator with p, for example? Okay, where here I have all the hats implicitly, so these are the operators. Well, so if you have f of x, so suppose now that we're talking about a function that can be expressed as a power series. So some coefficient times the identity, some coefficient times x, some coefficient x squared, and so on. Okay. So then to talk about the commutator, and remember that, sorry, this is very ugly. Remember that AB by definition is just AB minus PA. So in particular, if you had A, B plus C, this is going to be just AB plus AC. Okay, everything is linear. Okay, so in this case, this means that we'll have A0 and then the commutator of the identity with P plus A1 and the commutator of X in P plus A2 and the commutator of X squared in P, and so on. So we see some pattern here. So the thing we need to find out is what is the commutator of x to the n and p for some n natural number. Okay, so we'll just do it explicitly once, and then we know this forever. Okay, so there we go. So this is x to the n p minus p x to the n, and I'll just split the first term into two. Okay. So yeah, and the idea being that, well, I'll try to put this x on the other side, and I'll try to move all the x's to the other side so that then I can cancel with the second term, of the equation. Okay. And of course, we know that AB, it's going to be BA plus the commutator, right? Just from the definition, from here, we go directly there, right? So then we move the xp to one side, so we get, x n minus 1. And then what we get here, well, we get px plus I h bar, the identity, right? Minus p x to the n. So that's x n minus 1 px plus I h bar x n minus 1 minus p x n minus 1. And now we do the same thing again, where we want to move the next x to the other side, okay? And we'll do it again and again and again. So I'll just write this whole thing again. So we have x n minus 2, and then we have x p plus I h bar identity. Sorry. X n minus 2 x. Sorry, this is xn here and xn there. Okay, so I just rewrote the same thing again, and now we try to move this x there, and we're going to get exactly another term like this. So we get xn minus 2, and here we have IH identity plus sorry, what have I done there? Yeah, that's okay. Plus x, sorry, plus bx plus IH bar. And this, sorry, I messed up the brackets. Let me try to do this properly. So let's put here the x already. Let's do it like this and I'll try to be clever. Okay. So now here you have, now yes, px plus I h bar. X plus I h bar x n minus 1. There you go. X to the n. Okay. So this gives us x n minus 2 px squared plus, now this term will multiply with this, which will give us xn minus 1. So we have now two terms of this form, 2i h bar x n minus 1. Yeah, minus p x of n. And I think by now you believe me that if we do this enough times, iteratively, we'll end up here with px to the n, if we move all the x's to the other side, plus n I h bar x n minus 1 minus p x n. And then these two cancel, so we get just this term here. Nope. Just this term survives. Okay. So then let's continue here. So we copy. When we apply it now to the whole commutator, okay, I'll just write here the result we just got. So this was that x to the n p. This is n I h bar x n minus 1. So now when we apply this here, well, the first term is 0. And 1 gets, you get the identity here. Everything will be multiplied by I h bar. And then you get plus 2 x, and then you get plus 3 x cubed, and so on. Okay, and this, if you look at the original definition of f here, okay, then what we got is just a derivative of x with respect to x. So you get dx of f x. Okay, so that's what we have. So f of x p for any function of x that can be expressed as a power series is just this. And you can see, maybe this will be an exercise later, but maybe not, that the same applies if you put here a function of p. Then you get derivative in order to p of not f, but g of p. Okay. Good. So this is an ingredient that we will need. These are two ingredients that we will need later on. So now we take this, and let's go back to talking about dynamics in the actual dynamics in one dimension. So let's just recap the key things from the Schrödinger equation results. So we had that for uniform dynamics, meaning that in the end we saw that this meant, so it means that it doesn't matter when you start or the exact time at which you start evolving a system, just the duration of the evolution. And we saw that this means in the end that the Hamiltonian does not change over time. So there we have, in this case, then we have that the Schrödinger equation is of this form. I h bar g dt psi of t. And we saw that observables, so if in the same situation, if observables do not depend explicitly on time, then we have that the dt of the average, for example, of the observable is 1 over 8 h bar. And then the average of the commutator. So yes. And the other thing we saw was stationary states. So these are the ones for which these are the ones such that psi of t was just the psi of time equals 0, and then here just some oscillating phase, right? Where the frequency of oscillating was given by the energy levels of the Hamiltonian. Okay, so this is the eigenvalues of the Hamiltonian. This is what we saw last time, and now we're going to actually apply this to one specific Hamiltonian. Okay. So we could start with we could take any operator, any Hermitian operator to be the Hamiltonian, and we start with one that resembles the classical Hamiltonian of a free particle. Okay. And what I mean by this is that it's a system that is only subject to kinetic energy and potential energy. So in this case, we're going to have H being some, I'll write it down what this is, P squared. Okay, these two terms where this is going to be what I call kinetic energy, and this is going to be what I call potential energy. So what are the terms here? So here we have the momentum operator, right, square, and this is resembling the classical physics kinetic energy, where we have like the velocity square times the mass. And mu here is a term that is going to correspond to mass if we go by analogy with the classical one, but you can think of it as just being any constant. Okay. And v of x, this is just, don't confuse this v with the v for unitary. This is just some function of x that can be expressed as a power series. Okay, so this, what this represents, for example, is a particle like an electron has kinetic energy, and then there's some physics around that constrain the movement. For example, there is some electrical field that will pull it one way or the other. Okay. And of course, this only applies to this kind of energy terms that don't depend explicitly on the velocity, but just on the position of things. Okay, the reason for why this Hamiltonian, historically, it started with people knowing the classical Hamiltonian and trying to see what happens if you do the quantum version. So you can think of it as more reverse engineering, but you can think, another way to think of it is like, oh, well, we'll try this, see if it works, if it matches what we actually measure in the lab. And it does in this case. Okay, and then maybe much later on, we'll go into justification as to why this Hamiltonian, but now we'll just start with any Hamiltonian and see what works. Okay, also up to now, there's nothing telling us that this P, so the P operator was just a Fourier transform of the X, right? So why would it be the energy? Oh, sorry, why would it be the actual momentum as in mass times velocity in the classical sense? Right. So far, nothing tells us this, but today we will see some equations that are coming out of here that kind of justify this a posteriori. So in summary, we see it's just a Hamiltonian that is used a lot. Okay, so let's go with this. So what's the Schrödinger equation of this? Well, we have again H side T equals I H bar dvt t. So there we just get that, we just replace it directly. So we have p squared. Remember that this is an operator divided by this real constant plus p of x. H bar. Okay. But we want to see how how observables evolve. So we need to compute, as we saw before here, just this commutator. This will be the essential thing. So what we need to know is AH. Okay, and this is, well, A and the p squared over 2 mu plus v of x. And this is going to be 1 over 2 mu ap squared plus a v of x. And this is going to be very convenient because most of the observables that we'll consider, that they will either depend only on p or only on x, so one of these two terms will be 0. So for example, what happens to the position? Okay, so we have x and the Hamiltonian. Well, this is 1 over 2 mu x p squared plus x v of x. Okay. Now this term here, it's going to be 0 because v of x is just a power series of x. Okay, we're considering only well-behaved cases. So it's only power series of x, and x will obviously commute with every power of itself. And now here, to compute this one, we take p squared to be, we take it as a function of x, and we're just going to apply our result from before. So we're just going to apply this thing directly. Okay, so then this term here, so x p squared is going to be I h bar d d p of p squared of this function, right? Well, and that's just 2I h bar. So the whole thing gives us that xh is going to be I h bar over mu p. And now if we plug it into the evolution, so this means that the evolution of the average position x, well, this is, what was it, 1 over I h bar psi h psi. Well, this is now only 1 over mu, like the mass, and p. And this resembles what? This resembles classical physics, where the derivative of the position is the velocity, which is momentum over mass. Okay, so which is one of the reasons why we call p the momentum of the wave function, because when we look at how the position varies over time for a Hamiltonian that we think corresponds to a standard Hamiltonian, then we get the momentum as the answer. Okay, So now let's see how the momentum changes. So pH, again, it's going to be 1/2 mu p square plus p v of x. No, this is 0. And this, again, we're going to apply the result from before. So this is our function of x. So then p v of x is going to be I h bar d the x of v of x. Okay. Now, classically, what is the derivative of an energy, in particular of a potential energy? This is what we call the force. Okay. So in this case, we just take this quantity and we call it, we just give it a, a name f of x, which doesn't mean we're saying that this is the force, but it's like a convenient analogy, and it's just a name that we give it, right? It doesn't mean anything. So then we have that p over h is I h bar f of x, which means that if you look now at how the average momentum changes in time, well, then this is 1/I h bar. And here comes the commutator. So then this is just f of x. And again, classically, in classical physics, this is the case again, that the derivative of the classical momentum is the force. And the special case of this, because the momentum is classically is the velocity times mass, is that if the mass does not change, if d dt of m is 0, if the mass doesn't change, then what you get here is that the g of p is just mass times the acceleration, so the derivative of the velocity, and this is the force. Okay, so I'm just saying that force equals ma, which is like one of the most well-known things in Newtonian physics, for example. Okay, so now we have two very important results, which together make the Ehrenfest theorem. And that is that the average variation of x goes with momentum. This should be a capital P, and that's a capital X, sorry. And that the average variation of momentum depends on the force. There we go. And they exist the same statements for classical mechanics without the averages. Okay, so that's the classical analogy. Of course, we think that the world is actually quantum, and then in some regime, in the regime of very large systems, which we'll see later how this emerges, then we should recover the classical result. Okay. So now the last thing we can say is now, well, how does the wave function change? So what's the Schrödinger equation for the wave function? Like we said in the beginning, instead of thinking of the evolution of the stage itself, like the cat, we can think of just the evolution of the wave function. Okay, so we'll just apply the Schrödinger equation to the wave function. Then later on, when we look at specific examples for specific potentials v of x, then this is the one we work with directly. Okay, so that's right. Schrödinger equation for wave function. For the position wave function, well, and what we mean by this is we take we need to take, sorry, this I h bar d dt of psi, and let's put here the dependence on t explicitly. Okay, and now we're just going to sandwich this with the x from the other side to get the wave function. Okay, and because our Hamiltonian is split into two terms, we look at these two terms separately. Okay, so we have x. Let's look at the p squared term. Sorry. Yeah, that's right. Psi of t. Well, we know that is x as 2. Let's make it so p transforms the wave function as going from itself to derivative over x with I h bar, right? And now we just do this twice. Okay, so then we get t squared the x squared of f of x, sorry, psi of x and t. Okay, where here I just made the dependence on x explicit. I didn't change the state, it was still the same state as before. And then we had I times I gives minus I. I believe there should be an h bar square. Though here is only h bar in the book. Let's see what happens. Okay, x, u of x, psi of t. What do we do here? Well, the x should commute with everything that with this with this function that only has power series of x. So this means that we can bring the x there. So you only get p of x, but now small x. So let me make this really small x. Okay, and here the wave function. Okay, and of course it also depends on time still. There we go. Okay, and now we wanted the term on the right hand side. So what is x d dt of this wave function, or of this vector? Well, again, the derivative with time has nothing to do with x, so we can, sorry, this should not be there. Chook. So we get d dt, and now the wave function on x and t. Okay, good. And in some places I made this dependency on x explicit, and in some places not, but you can think that it's always there. Okay, so overall, we get, if now we take the full Schrödinger equation, what we get, we'll get the following. And you can do it explicitly, but it's really just taking this, all these terms. So you get minus h bar squared. Yeah, there was a typo in the book. U dx squared of check x and t plus some u of x and t psi of x and t equals I h bar p dt of psi of x and t. Okay, so this is the Schrödinger equation for the wave function itself. So now there's no operators left anywhere. Sorry, this t should not, there's a t too many. This u only depends on, u is a v, so, and it only depends on, the potential only depends on x. Okay, good. So now we have a differential equation where we have this, so the second derivative on x, the first derivative on time, and just the function itself. And solutions for this will be of the, depending of course on the form of this thing, but they will generally be wave-like solutions, because it's also the same kind of differential equation that we see for classical waves, for example. The difference here being that this thing can be a complex number. So if we look at stationary states, which we talked about, we saw that they need to be in general of this form, psi of t equals e minus I hk t, and here the h bar, I don't know if I put the h bar the first time around, let me see. Chuk, chuk. Yeah, missing the h bar there, there we go. So I have something of this form, and you have psi of time equals 0, right? But it can still depend on x, right? Well, we'll see in a moment. So what happens when we put the x on both sides? Well, then you get to get the wave function of x and time. Then this thing, so this exponent here does not depend on x at all, so it survives, akt of h bar, and then you get here x psi of t equals 0, which is just e minus I ak t of h bar, and it's the wave function of x and time equals 0. Okay? Which means that when we look at the stationary states of the Schrödinger equation in a line, we'll have something that depends only on the position, and then the dependence on time is only going to be this this phase, this global phase. Okay? And now in the what we'll do next week is now to give explicit examples for this potential and try to find what the stationary states are. Okay, this is a very, very, very important problem in physics and in chemistry and in pharmacy, even relevant for agriculture, which is try to find the stationary states of some Hamiltonian, which means in the end, what it represents is try to find the states of low energy of some system, of some physical system, which means try to find the states in which this physical system actually is. So this has countless applications, and it's one of the, it's in fact the main promise of quantum computers, is that they will be able to solve this problem faster. Okay, but again, it's more of an intuition at this point, and there's no concrete results saying that quantum computers can actually do this faster, but we will talk about this next week. Okay, thank you everyone.